Hi, everyone. So now let's look at the apparatus for our third experiment, a quantum eraser. Really neat experiment, by the way. Of course, the equipment is almost exactly the same as what we've used for the second experiment. That is, it consists of our entangled photon source, and then some additional optics here, and our photon counting detectors. There are two changes we're going to make for this particular experiment, and I'll try to mention them now so you can be thinking about them. One minor change is that we've put a second polarizing beam splitter into our apparatus. Now this is on the gate path, like so. The second thing is that when we go to do the experiment, we'll introduce this item, a polarizing interferometer, into the signal path. And we'll take a close look at that in a moment. One other detail which is more minor is that we'll, get out of the way, is that we'll be looking more closely when we set up these optics. In particular, might have to adjust this component, which we didn't use before, which is a birefringent plate. All right. Let's take a closer look at the interferometer now. 1 second. Okay, now we can look at it a little bit more closely. So here's the polarizing interferometer. And the most important components are this component here and this component here. This is a polarizing beam displacer. What it does, it's a kind of prism. When light enters, it splits the light according to its polarization components. The vertically polarized component goes straight, whereas the horizontally polarized component is first deviated, and then it's redirected to come straight out as well. The result is that these two beams are separated in space by about 1 centimeter. After that, they both pass through a polarization rotator and come to a second beam displacer, but this one is turned around the other way. And so what it does is it puts the two beams back together. Why do we need this central component, the polarization rotator? It's a little detail. If we want the two beams to come back together, then the beam on this side, on the right to me, has to be horizontally polarized when it enters the prism, and the one on the left has to be vertically polarized. Only then will this put them together. However, that's exactly the opposite of what the first beam displacer produced. So we're going to use a polarization rotator set at 45 degrees to rotate the polarization of each component by 90 degrees, i.e. to turn the horizontally polarized component into a vertically polarized component and vice versa. In any event, then this brings them together. So these two components with the rotator, they are the entire Mach-Zehnder interferometer that we talked about in experiment 1. One other thing, one of these beam displacers can be moved slightly. There's a motor here, and when the motor operates, it will very slightly turn this beam displacing prism. And what that does is it has the effect of changing the path lengths of the light from this point to that point, but it doesn't change them equally. One of the path lengths changes more than the other. So it changes the phase delay between the two paths that's experienced when they recombine. This motor here can be controlled electronically, and so it's controlled by this controller here, which in turn is programmable and is controlled by the computer. Okay, after the light leaves the polarizing Mach-Zehnder interferometer here, we have to do one more thing. In the course of going through these displacers, the entire beam has moved over by about 1 centimeter. But it would be convenient for us if when the beam leaves this system, if it's going along the same path that it was traversing before. because we're just going to insert this into the signal path. So we have two mirrors here, and their only purpose is to shift the beam back over by 1 centimeter so that it's following the original path, okay? And by the way, the thing that we're most likely to disturb if we're not careful is this mirror or maybe that one. If we bump them, then the beam won't be going in the right direction and it won't go to the detectors unless we realign it. So try not to bump it. In fact, when you handle this, and you're going to have to handle it once, just handle it by these steel rods that are attached to the base plate, and just slide it along the table. You don't even have to lift it up. And so you can slide it into position and then out for use, and then lock it down, and then slide it out of position later. That's described in a later video. Okay, that's the interferometer.